be going through some practice problems in here for 323's beam analysis. And so these are the beam analysis calculations assignment here. What we want to do first is we want to bring up the engineering formula sheet. And so the section we want to end up going to, we're going to be scrolling down here. We're going to be looking at structural analysis, which is section 12. So 12.0 structural analysis. If you end up getting any questions like this on the EOC, remember we can always press Control F and then we can type in beam. And then that will end up showing you the beam formula, right? This is the beam analysis. And so that's why we search beam there. As you can see, we have these different situations or these scenarios. So if you have a concentrated force, you're going to end up using these equations to determine the reaction forces or the moment or also the deflection. We haven't talked about deflection yet, so don't get too worried about that. But then also if you have a uniformly distributed load, then you'd end up using these equations. If you have two concentrated forces that are both placed distance A, so these are both placed, so one's here with distance A, and then there's also this distance A as well where this other force is located, then you'd end up using these equations. And then finally, if it is a concentrated force that is offset, so it's not in the middle or it's not two separate forces that are symmetric, then we're going to end up going these equations here in this scenario. All right. So this is our best friend here. We want to end up using these formulas that we're going to be plugging in the values. We're going to start off with question 1 here. And so it tells us that there is this picture here. So this is our beam diagram. The beam is in static equilibrium, meaning that there's no acceleration. The sum of the forces equals 0, sum of the moments equals 0. They tell us P1 is equal to 520 pounds. And so they want us to determine the reactant force at point A as well as point B. So there's going to be the y-axis forces that are going to be occurring there. So let's go ahead. Let's get ready to begin. We see that the overall distance of this beam is 16 feet. And that force, P1, concentrated force, is going to be placed 8 feet in. So let's go ahead. Let's begin. So I'm just going to write number 1 here. And then now we want to create this free body diagram. And so since we have 16 feet, I'm going to have each of these represent 2 feet. So 2, 4, 6, 8, 10, 12, 14, 16. Then we'll go right here. Go ahead and create that. So 2, 4, 6, 8. That's where we have our concentrated force P1. So I can end up writing down how many pounds of force that is. We're also going to have, so this is point A, right? So we're going to have FXA, and then we're going to have FYA. Now keep in mind, why is this FXA on here? That is because this is a pin support. So the pin supports have both an X force and a Y force. Then whenever we look over at this side here, point B, that's just going to be the Y support for our roller. That's going to be FYB there.
This is correct.
And so now let's go ahead and put in for P1, it's going to be 520 pounds. So remember, we'll write that in. And then if we use the pound symbol, that just represents pounds. So don't forget about that. Let's just double check everything. Make sure that we're good to go here. Yep, everything's looking good. So they want us to determine in the box below the reactant force at B and the y-axis. And so if we end up going in here, we'll end up saying this is scenario 1 here. And so RA is equal to RB. So those values are the same for those reaction supports where RA is right here. So that's the vertical force there. And then the RB is this vertical force here. And basically what this is going to be equal to is just our applied force divided by 2. And so we can end up going back to this. And we can end up saying equation 12.1. So I'm going to go ahead and write this equation. And we're going to put in parentheses 12.1 states that RA is equal to RB, which is equal to P divided by 2. So in this case, I called RA and RB. RA is FYA. So this is basically FYA is equal to FYB. And then that's going to be equal to 520 pounds divided by 2. So now if we end up bringing out the good old TI-84, let's get that guy fired up. We can go in here and we can put in 520 divided by 2. And so now what we know is that it's going to be equal to 260 pounds. So we can go ahead and write these values in here. So 260 pounds here. This guy's also equal to 260 pounds. And so that's just in terms of those those forces acting in the y-axis for the support. As you can see here, FXA, so although this isn't in the equation, that we just used, remember the sum of the forces in the x-axis, it's all the forces that are occurring horizontally, and Fxa is the only force that's occurring there. So if we go Fxa, that's going to be equal to 0, right? Because there's no forces to actually sum up. And so what we can also put here is that guy is equal to 0. So I'm just going to cross that out. All right, perfect. But that's number one. Let's go ahead and let's check out the second example here. So if we go back to this, we can scroll down here. We're going to put in our value there too, by the way, 260 pounds. So question number 2, we're going to actually skip that one because that's exactly what we were just doing. We'll go ahead and go to question number 3 here, which is going to be the simple beam with a uniformly distributed load. And so this uniformly distributed load, remember, we calculated that out in activity 3.2.2. The uniformly distributed load is equal to your tributary width multiplied by that total load that we end up finding. And so remember, the total load equation is from the IBC, the International Building Code. We were using the 2012 edition. Usually it's dead load plus live load or the snow load. But anyways, that's where we're getting W1, just so you guys make sure that you don't get too confused. You're like, what is W1, you know? But this is what it ends up looking like on the beam, that uniformly distributed load. And so what they tell us is W1 is equal to 142 pounds per foot. And then they want us to approximate W1 as a concentrated load and then determine the reaction forces at point A and point B. And so we have a pin here, we have a roller, and then we have this uniformly distributed load now. Let's go ahead and let's create our force diagram. I am just going to keep this as number 2 because it's just our second example problem. So let's go ahead and do that. Let's make sure that we have this overall length too. I'm seeing the overall length is 16 feet. So I'm going to use that same scale where one grid represents 2 feet. So 2, 4, 6, 8, 10, 10, 12, 14, 16. So there we go. We got this guy down here. And so now this is where we want to look at these supports. So this is the pin support. That's a roller support. You'll remember the pin supports. We have FYA here. There's also going to be FXA. We're also going to end up having FYB there. And then we're going to have this uniformly distributed loads. So I'm just going to go ahead and draw this guy out. Okay. So we have it there. And then W is going to be equal to, as we're saying, W in this case is 142 pounds. So that's pounds per foot is what we've got, right? Because that is a uniformly distributed load. And so what this tells us, and also guys, so sorry, this is something I also should have included here. This was 8 feet there, and then this total distance is 16 feet here. I should be making sure I'm including dimensions. Should be the same case here where we've got that 16 feet included on this. So the distance from here to here, 16 feet. But with the uniformly distributed load per foot that is applied, that's going to provide 142 pounds of force. It's basically what we've got here. All right. So all we're going to end up doing for this is we're going to go to our engineering formula sheet. As you can see, this is scenario 2 here. So we've got scenario 2. And to find the reaction supports, load, so the reaction forces, we want to end up just using this equation right here where this is W times L, or I guess you could say that's omega, lowercase omega, times L divided by 2. So that's equation 12.4. So that's what I'm going to go ahead and do. So I'm going to write down equation 12.2. And then what that states is that F, or RA, is they have that as the reaction, is equal to RB, which is equal to omega times L divided by 2. Remember, this is just lowercase omega is what that W looks like. And so now if we end up taking this basic equation and we plug in our values, instead of RA, I have FYA. So when I wrote that down, that's equal to FYB. And that's going to be equal to omega. So that's 142 pounds per foot multiplied by that length of 16 feet. Right. And what ends up happening, we divide that by 2. What happens with these units of feet is they cancel so that we're left with just a value of pounds or a unit of pounds. And so now if I end up bringing the good old TI-84 back up, we can plug this in. So we got 142 times 16, and then we're going to divide that by 2. So that is 1,136 pounds. And so that's what that guy's going to be equal to. So FYA is the same as FYB. Both of those are equal to 1,136 pounds. So we can end up writing these guys in 1136. Remember, you can use the pound symbol if you want to. This one's 1136 pounds as well. Okay. Now the other thing, FXA, just to be thorough with this, the sum of the forces in the x-axis is equal to 0. We'll say to the right is going to be positive. So this is going to be plus FXA. And as you can see, this is the only force that's acting in the x-axis. So FXA is equal to 0. And so that's why we can do this cross through and then put 0 there, because that guy is equal to 0. All right. So there's that one. Now we're going to go to the next problem. This one's going to be a little bit more of a challenge. And what we're going to do is it's going to actually be a combination of two of these scenarios. And so as you can see here, we've got P1 here. Also got P2. These are both occurring 4 feet away from the supports. And so this is 4 feet away from point B. This one's 4 foot away from point A. Then we also have that uniformly distributed load. And so this is basically, not only is it just this situation here, but it's this situation and this situation as well. If that is the case, what we can actually do is add these. So if we have RA equals RB equals omega times L divided by 2, and this one is RA equals RB equals P, we basically are going to take this and then add on P at the end of that to get those. So if there's these two scenarios, if it's a combination, we have to add in whatever is after this last equal sign here. And then we add those two scenarios together. All right, so let's go ahead and let's get ready to begin. I'm just going to write down number 3 because this is just example problem number 3, right? For you guys, whenever you're going through this, make sure you're writing the actual correct question number for that. But we'll pop back into here. And so we've got this set up here. This is going to be 16 feet long overall. So we're going to go ahead and do the same thing as before, where each of these is going to represent 2 feet. So 2, 4, 6, 8, 10, 12, 14, 16. There we go. We got this. I have one of my concentrated forces. I'm going to drag this out a little bit. P1 there, and then 4 feet away from point B, we're going to have P2. And then remember, we've also got omega in here, or W, which is that uniformly distributed load. So we can go ahead and draw that guy in too. So it's a combination of these. So we got W there. So now let's go ahead and put in, so W, P1 and P2. So W is 109 and then 258. So 258 pounds, 258 pounds, and then 159 pounds per foot. So that's 159 pounds per foot. That's 258 here, and then also 258. So now let's look at our reaction forces. This is a pin. So a pin has not only a Y support, but also an X support. And then our roller is just going to have a Y support. What I'm going to do this time is I'm going to differ this a little bit. I'm going to have RAY, and then I'm going to have RBY. And then I'm also going to put over here RAX, because that's the X component of the reaction force. Now, we can switch this up a little bit, just as we were talking about the sum of the forces in the x-axis is equal to 0. If we make to the right be positive, then we can end up looking at this. So we have RAX. So that X component of the reaction force, right? That's the only force that's actually happening in the x-axis. That's going to be equal to 0. And so now what I can do is I can do a cross through this and put that equal to 0 there. All right. So now let's go ahead and get down to this equation with the Ethereum formula sheet. As we're looking at this, we said it was a combination of equation 12.4 as well as 12.7. Now, guys, this is a mistake that I just actually noticed. This is 12.4 here. So I'm going to go ahead and put today's date and my initials because I did make that mistake. So that is 12.4. But what we're going to be using in this question is going to be a combination of equation 12.4 and also equation, if we look at this, it's going to be 12.4 as well as equation 12.7. So it's going to be both of those. And what this is going to be is it's going to be RA equals RB, which is equal to omega times L divided by 2. So that's that first part, right? And then we're going to add on P at the end here. So let me show you guys this. So omega times L divided by 2. and then you just add on that second equation, right? Whatever is after that equal sign. And so this is going to allow us to actually solve for RA and RP here. And so now we can go ahead and plug these values in here. So we're going to end up switching this up. So RAY is what I actually called that force RA. And then RB was RBY. And then that's equal to, so omega. So omega is 159 pounds per foot. Now we're going to multiply by that total width here. And so if we go back to this guy, we'll end up seeing that that is 16 feet here. And so what I'm also going to end up doing is I'm going to also write this out. So this is 4 feet here. This is also 4 feet here. And then this total distance here, we could actually just do this. We could just put this in here. So if this is 4, we're going to have 8 feet here. So we could do that. So now that's multiplied by the length. So our total length for this is 16 feet. And then we're going to divide that by 2. These units of feet are going to cancel out. We're going to be left with the unit of pounds. Then I've got to add on P. So our values for P, those are the same. It's just 258 pounds there. And so now since we have pounds as this unit, we can add on this other value of pounds as well. So let's go ahead and get the TI-84 back up again. And we can punch this in. So 159 times 16, that divided by 2 plus 258. That's going to end up giving us the reaction supports. Each of those are going to be equal to 1,530 pounds for that. So then now if we pop back up here, we can go ahead and write this in, 1,530 pounds. And this guy's also equal to 1,530 pounds. All right. Anyways, I hope this video was helpful. We went through 3 of those practice problems there. Remember, as you're going through this, your engineering formula sheet is your best friend on this. All right. Hope that video was helpful though. Happy calculations. See y'all later. Bye-bye.